Algebra lesson 7-5. Now that we spent quite a bit of time working with different types of solving systems of equations, just want to look one more time at a situation for systems of equations. Supply and demand. There's a break-even point for supply and demand. As you think about it, if the demand is very high and the supply is very low, then it's going to make the cost of things go up. As supply increases and there's more and more of the object, the demand will tend to go down. And we don't really want to have too much supply with very little demand. We can't charge a higher price when there's too much supply and not enough demand. So companies will purposely try to keep on this side of the graph where they can keep the demand very high and the supply very low. Or maybe they want to be optimizing it where the demand and the supply are the same so that you sell every single item. It's far better to be on this side than to be on this side where your supply is higher than the demand itself. Typical responses are like during most holiday times when the Wii comes out or the new PlayStation or a hot new game and there's simply not enough. There's a huge demand and just not enough supply, then this is where the companies make the most money. Nike will do this when they re-release Jordans. Recently there's been some problems at a mall where people were freaking out trying to get some shoes that were released. There was a very low supply, it was low, but the demand was very high, and thus it caused people to go into a frantic. Now, most of the problems that we worked with all had solutions. It is possible for some very special scenarios to exist. And the number of solutions that you will have in a linear system can be a few different options. That's all we have. We'll have the type of options we've been working with lately, which is where we actually have one solution that we come up with. But we could also have a situation where, this is our typical, this is what we've been dealing with, where the two lines cross and it creates one solution. But another form is when the lines are parallel. If the lines are parallel, they will never intersect. And if they never intersect, how could they possibly share a solution? They never will. They have to actually contact each other to make a solution. And then our third possibility is the idea of what we call coincide. There are infinite solutions. It's hard to see, but there's actually two lines here. I did one in green, and I did another one in dotted red to kind of show through. But this is two lines, this is two lines, there's also two lines here. They just happen to be exactly the same line. So that means that every single point is going to be a solution. That's why there's an infinite amount of solutions. If you think about this, in order for these to cross, they have to have different slopes and different y-intercepts, unless the y-intercept is the location where they cross. So let's preface that. Unless the y-intercept, I shouldn't say y, different y-intercepts, unless the y-intercept is the solution. That's the only time that would be an exception to the rule of that. Then over here for parallel, they are going to have the same slope but different y-intercepts. And the reason they have the same slope is because that is what makes them parallel. They have to be the same slope to be parallel. And in order to be the exact same line, they must have the same slope and the same y-intercept. They may not appear to be the same. For example, you might have one that says the slope is 2/4 and the other one says the slope is 1/2. But that's still the same. 2/4 and 1/2 are the same. So I like to refer to this as one, none, or a ton of answers. Those are your three possibilities. One, none, or a ton. That's all you can ever get. So our first example, let's show that this actually has no solutions at all. It appears in this situation that this particular problem is set up for us to use linear combinations. They're both in standard form. There are certainly some adjustments that we're going to make. I would probably multiply the bottom by -2. If we multiply the bottom by -2, we will get positive 6x plus -2y is equal to -14. Now I can bring the top equation down like we've done in the past, and we'll have negative 6x plus positive 2y is equal to negative 8. And as soon as we try to use our linear combinations, the 6x and the negative 6x will cancel out. The negative 2y and the positive 2y will cancel out. So we're really left with nothing on this side. And over here we get negative 14 and negative 8, which is negative 22. It is impossible for 0 to equal negative 22. That's an untrue statement. So there are no solutions. When you use linear combinations, what will happen is both the x's and the y's will end up canceling out, and it'll equal a number that it can't equal. So no solution. Alright, we can show that there are infinite solutions. Again, I'm going to use linear combinations. Make this a little bigger. Now, with linear combinations, I want to make sure my coefficients match up. So I'm going to multiply the top by 3. And if I multiply the top by 3, I should get negative 3x, positive 6y, equals negative 6. Again, we go to put them together. The 3x and the negative 3x cancel. The negative 6y and the 6y cancel, so there's nothing on this side. And then 6 and negative 6 cancel. Since 0 is equal to 0, that means that these are both the exact same equation. If you think about it, you could have multiplied this top by negative 3. That would have produced positive 3x, negative 6y, and positive 6. In other words, the exact same equation. So these two equations coincide. There are going to be infinite solutions. And that doesn't mean that any number works. It just means that there are so many solutions we can't write them all down. Alright? Solve and interpret this scenario. It seems as if they are both in what we would call standard form. Maybe an adjustment could be made. We could multiply the bottom by 2. If we multiply the bottom by 2, then we would have negative 6x plus positive 2y is equal to 24. We would have the top to bring down. We could change that to plus negative, which is 6x plus negative 2y is equal to 10. And now we're ready to add them together. The negative 6x and the positive 6x cancel. The 2y and the negative 2y cancel. And we get 0 is equal to 34, which is not possible. So this should be no solution. If we take a moment to graph it, each of these is in standard form, which means we can find a slope. So dealing with this one right here, we would say the slope is opposite A over B. It's negative 6 over negative 2, or positive 3 over 1. And the y-intercept is C over B. So the y-intercept is equal to 10 over negative 2, which equals negative 5. So I can graph that. And do the same thing for this second equation. It has a slope of opposite A over B, which B is a 1. That would be 3 over 1. So you'll notice the slopes are the same, and if the slopes are the same, it's either going to be parallel or coincide. And then our y-intercept is 12 over 1. Which is 12. So a quick adjustment to our graph, ungroup it. It's acting a little slow tonight. I'll move this down a little bit. That will allow me to graph. The first one has a y-intercept at negative 5. So 1, 2, 3, 4, 5. There's the y-intercept to negative 5, and it goes up 3. 1, 2, 3, and right 1. 1, 2, 3, and right 1. 1, 2, 3, and right 1. So it's definitely enough to make my graph. And the other equation has a y-intercept at 12. So 2, 4, 6, 8, 10, 12. I don't really want to go up 3 and right 1, so I'll go down 3 and left 1 to keep it on the graph that I have. And now I've got enough points that I can see exactly what's happening here. And as you look at the two graphs, it's a mistake. As you look at the two graphs, it appears as if they are parallel and they will never cross each other. And because they'll never cross each other, they have no solution. So again, you can have one solution, no solutions, or a ton of solutions. One, none, or a ton. That's it.